Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 12 students who are studying trigonometry and advanced functions. In this video, we'll look a little bit more at radians and why we use them now to measure angles, and we'll make a connection between radians as angles and the arc length around a circle. So here's what we're exploring just visually. An arc is a circular path traced around a circle, and the length of that is called the arc length, and I've highlighted it here in red. And we want to explore the connection between the length of this arc and the angle that is subtended by that arc. And so I'm going to open up a piece of software here called GeoGebra and explore that a little more carefully. So on this diagram, you can see that again, I've got the red highlighted arc, and we're interested in the length of that arc. And then I've highlighted the angle down here in a sort of gray tone. And as I increase the arc length, you can see that obviously the angle gets bigger. And as I make a smaller arc length, the angle gets smaller. So over here, hopefully you can see all this. Over here, I've got the computer doing some quick calculations. So first of all, it shows me at all times the radius of the circle. And the radius of the circle, obviously it doesn't change because I'm not changing the size of the circle. But it's also showing me the arc length. So as I change the arc length or increase the rotation, you can see that the arc length increases, and when I decrease it, it decreases. So that's the length of this red arc. And we'll look at what this is doing in just a second. So the first thing I'm going to do is I'm going to try to trace an arc length that is equal to what the radius is. So the radius is 4.34, so I'm going to try to get as close as I can to 4.34. Hey, pretty good. So this arc length is exactly equal to the radius, which is 4.34. And so by definition, because the arc length is 1 radius, we would say that this angle is 1 radian. If I double the radius, so 4.34 doubled is about 8.68. And all right, pretty good. So what I have here is I've got an arc length of 8.68, which is double the radius. So I can draw the radius length exactly twice on this arc length. This angle here, excuse me, would be considered to be 2 radians because there are 2 radius lengths on that arc. And if I keep going, if I triple it, so if I take the radius and I triple it, that would give me a value of about 13 point a little bit. And so that would be an angle of 3 radians because there's 3 radius lines. And of course, if I go to the halfway around a circle, so if I have an arc length which is half the circle, then we know that the radian angle would be pi, or 3.14. And if you've noticed, what's happening over here is that I'm doing a quick calculation, and what the calculation is doing is comparing the arc length to the radius. In other words, this calculation is telling me how many radius lengths fit into that arc length. So here, exactly 3.14, so roughly pi radius lengths fit into that arc length. So really, this calculation, arc length divided by radius, is telling me how many radius lines fit into that arc length, which is actually telling me the radian measure of that angle, because that's what radian measures. A radian angle measures how many radius lengths you can fit into the arc length of that angle. So this calculation, arc length divided by radius, is what we need for this particular video. So this is what we just saw, arc length and angle. So we know that if we take the arc length and we divide by the radius, we're going to do a calculation which will tell us how many radius lengths fit into that arc length. And that is the definition of what an angle is in radian mode. So to simplify this formula right here, the angle in radians is equal to the arc length over the radius. And so that's the formula that connects arc length to angle, as long as your angle's in radians. So let's have a look at that formula a little more closely. So here it is, the formula you need to know, that the angle in radians is arc length over radius. But of course, we could rearrange it into these two forms. So if I multiply by r, now this is a formula that tells me that arc length is radius times angle, and then rearranging it one more time to isolate r, here I can calculate the radius if I know the arc length and the angle. But in general, you memorize one formula and then you rearrange it when you need it. Just a quick note about this one. If I were to rotate the entire circle length, so if I were to go from here and rotate all the way around, I've gone a full circle. And the arc length of a full circle is actually called the circumference. You should remember that from a previous grade. So the arc length of a full circle, also known as circumference, is equal to the radius of the circle times the angle. Well, we know from our previous discussion about radians that a full circle has an angle measurement of 2 pi radians. So we can see here that circumference is equal to 2 pi r. So that formula that you've used for years to find the circumference of a circle is actually based on what we just learned about arc length and radian angles. So that's sort of interesting. But let's just look at some questions involving this formula. Make sure you're comfortable using it. It says an arc length of 14.3 centimeters is measured on a circle with radius of 4 centimeters. What angle is subtended by the arc? So really quickly, you don't need to draw a sketch, but I like, sometimes it's nice to help make sense of things. So we have a circle with radius of 4 centimeters, and there's an arc length of 14.3. So 4, I'm just kind of pretending somewhere around here, somewhere. So this arc length, I tried to just roughly estimate where, if this is 4, then I sort of eyeballed 4 plus 4 is 8, plus 4 is 12, plus 4 is, oh, so I went way too far. Whatever. Diagram not to scale. So the question asked me to find this angle if I know that this arc length is 14.3. So we're going to use the formula, and again, to remember a formula, write it down every time you need it, and then eventually it's not a case of memorization, you just know it. So I need to find the angle. I know that the arc length is 14.3 and the radius is 4. So a quick calculation, just divide, and I get 3.575, or I guess we could round that if we wanted to. So what that means is that, in fact, 3.575, about 3.5 radius lengths fit into that 14.3 arc length, and so this angle is 3.5 or 3.6 radians. Next question. An angle of 0.8 radians is measured on a circle with radius 2.7. What arc length would be subtended? So this time we know, what do we know? This time we know that the radius is 2.7, and we have an angle of 0.8 radians. So that's not even 1 radian, so that's not very much. And it asks us to find the arc length. So let's use the formula. And you can certainly rearrange it. So I want to know the arc length. So if I rearrange it, now I have a formula that will help me calculate arc length. So the radius is 2.7. The angle in radians is 0.8. And so a quick calculation will tell me that the arc length is not even as big as the radius. It's 2.16, and it would be in meters, because that's the measurement used for the radius. So this arc length is 2.16. Next question. If an angle of 4.8 radians is subtended by an angle, if an angle of 4.8 radians is subtended by an arc length of 24 millimeters, what is the radius of the circle? So this time, what do we know? We know that we have an angle of 4.8 radians, so that's a pretty big angle. I'm just going to kind of estimate that it's about here. We have an angle of 4.8 radians, and the arc length, so this arc length is 24 millimeters, and it asks us to find the radius. So, using the formula. So there's the formula. Now, because I want to solve for the radius, I can rearrange this to say that the radius is arc length divided by angle. So the radius is 24 divided by 4.8, So the radius is, oh, I should know this, 5. So the radius is 5 millimeters. So, and what that means again is that if this length here is 5, then I can trace, sorry, yeah, if this length here is 5, I should be able to trace 4.8 of those along this arc length. So 1, 2, 3, 4, and 0.8 more. That's what it means. So hopefully this is helping you understand a little bit more about why radian measurements are more natural to a circle, because it's telling you something very specific, and it's telling you something about the arc length and the radius of the circle. So let's look at another question, but this time we'll use an exact angle instead of a decimal angle. It says, what arc length subtends an angle of 11 pi over 12 on a circle with radius of 8? So this time I'm going to do without a diagram. So here's my formula. So I know what the angle is, and I know what the radius is. So I'll rearrange the formula because I'm solving for arc length. So I know that arc length is equal to the radius, oops, lost my information, which is 8, times the angle, which is 11 pi over 12. So all I have to do now is this bit of math. So I'll do it where I'm assuming that you want an exact answer, meaning I'll leave things in fraction form and I won't calculate out the value of pi. So that would just have me do kind of 8 times 11 pi, which is 88 pi, and 1 times 12 is 12. So there it is in exact form, but of course it needs to be reduced. So I would reduce 88 over 12, which gives me 22 over 3. So in this case it would be 22 pi over 3. So that would be my answer in exact form, and my units were centimeters. So the arc length is exactly 22 pi over 3 centimeters. But if I wanted that in decimal form, I would just in my calculator do 22 times pi divided by 3, and then round to an appropriate number of decimals. So this is really close to 23 centimeters. Okay? So let's try another one with an exact value. It says an arc length of 8 pi subtends what angle on a circle with radius of 12 centimeters? So the arc length is 8 pi. Oops. So the arc length is 8 pi and the radius. So here's my formula. And this time I know the arc length and the radius, so I don't have to rearrange anything. So 8 pi divided by 12. So the angle is 8 over 12 reduces to 2 over 3, so 2 pi over 3. So there's the angle in exact form, 2 pi over 3. And again, if you wanted that in decimal form in your calculator, you would calculate 2 times pi and then divide by 3. So about 2.1 radians. So now that we've explored that formula quite a bit, now we're going to connect the idea of angles and arc length to something called angular velocity. So angular velocity measures how fast something is spinning in terms of what angle it passes through over a certain time period. So just to make that clear, here's an example. I might have something that's spinning at a rate of 5 pi over 8 radians per second. So every second it turns by this angle. That's what angular velocity is. So if we know the angular velocity, we should obviously be able to calculate the rotational velocity. Rotational velocity is a measurement of how many full rotations it goes through over some time period. So let's actually do that for this question. If this is the angular velocity here, let's calculate the rotational velocity. So if I'm rotating by 5 pi over 8 every second, I want to know how long will it take me to go an entire circle? So what time period would have me rotate a full circle? So a full circle we know is 2 pi radians. So you could say that's one rotation or one revolution. So if I have 5 pi over 8 and I want 2 pi, so let's just do some division. Well, actually, let's think this through. So if I have 5 pi over 8, that's 1 second. Let's look at what happens in the next second. In the next second, so in 2 seconds, I'll go 10 pi over 8, and 10 pi over 8 reduces to 5 pi over 4. So I'm not at a full circle yet. So now let's look at 3 seconds. So this is 2 seconds. Let's look at what happens in 3 seconds. So in 3 seconds, 5 pi over 8, 1 second, 2 seconds, 3 seconds, that would be 15 pi over 8. And of course, we know that if I got to 16 pi over 8, that I would have a full revolution because that's equivalent to 2 pi. But I'm not going to get there. So we know my answer is somewhere around 3 seconds. So how do I find it exactly? So now we're going to do just some basic math. 2 pi is equal to some number of rotations by 5 pi over 8. So 5 pi over 8, I want that to happen a certain number of times to get to a full rotation. And again, k is just standing in for, I don't know how many times. I know that it's about 3 because of this logic I did up here, but I'm not sure how many. So k represents that number I'm looking for. So how do I find k? Well, now that I've set it up with a formula, I know that I just have to divide 2 pi by my angle, and that'll tell me how many times I rotate that 5 pi over 8 angle. So it looks kind of complicated, but don't sweat it, it's fine, because remember I could write this as 2 pi divided by 5 pi over 8, which means I can just write it as, sorry, just give myself some more room, 2 pi over 1 times 8 over 5 pi. So that's going to give me 16 pi over 5 pi. And of course, the pi's will cancel out. So 16 over 5 equals k. And let's get that as a decimal, 3.2. So what that means is that this rotation of 5 pi over 8, which happens every second, I need this rotation to happen 3.2 times to get a full circle. And so that means that a full circle or a full rotation will happen in 3.2 seconds. So the rotational velocity of this particular question, we could say that it's one rotation in 3.2 seconds. That's the rotational velocity. Now, typically, so one rotation in 3.2 seconds, that's not really the typical way. Typically, we would write what it is in 1 second. So I'm just going to divide. So it's 0.3125 of a rotation every second. Okay? So, again, we're talking about angular velocity, which is some angle over a time period. And what happens is, if we know the radius, we can also calculate something called the distance traveled over time. So I've got this here just to sort of visualize this, that if you picture a dot at the end of this spinning arm, as I rotate, that dot is actually going to be traveling along an arc length. And we can calculate what total distance that calculates if we know the radius, because we can just do an arc length calculation. So the distance traveled over time that that point goes through, well, distance traveled over time is just velocity or speed. So if we know the radius and we have angular velocity, we can also calculate distance traveled. So let's explore that. Why did I put this here? Oh, I know why. Okay. So the reason why the radius is really important here is, imagine a point at the end of this particular spinning arm. and a point at the end of this particular spinning arm. As I spin them, it's pretty clear that this point, it's going to travel a lot further than this point because this is a much larger radius. So the radius is very significant when calculating actual distance traveled. However, the angular velocity would be the same. Yeah, I think they're traveling at the same rate. It's the same little flash program here. Oh, wait, I got this one going fast. If the angular velocity is the same, this radius is very important. So let's look at a question and see how to do this one. A fan blade is rotating at an angular velocity of 5 pi per second. So every second, the angle it rotates through is 5 pi. And it says, how many full rotations will the blade revolve through in 1 minute? So first of all, let's figure this. I've got 5 pi radians in 1 second. So let's figure out how many radians we would go through in 1 minute. So we know that there are 60 seconds in a minute. So if I multiply by 60, that would be 300 pi radians in a minute. So in 1 minute, this blade rotates through an angle of 300 pi. So how many full rotations are there in 300 pi? So we know that there's 2 pi in 1 rotation. So if I take 300 pi and I divide by 1 circle, it'll tell me how many full rotations I have. And in this case, obviously, 150 full rotations in 1 minute. Now, another way we could have approached this question, because it says 5 pi, we know what 5 pi looks like from our discussion about radians and sort of the trigonometric side of them, that this is 1 pi, 2 pi, 3 pi, 4 pi, so here's 5 pi. 5 pi is equivalent to 2.5 full circles, or full rotations. So every second, it's 2.5 full circles, so I could have taken 2.5 and multiplied by 60 and also got the same answer. And that one works really nicely in this question because it's such a nice angle to work with. But generally, the method is to divide by 2 pi when you know what the angle is, and that'll tell you how many full rotations. So let's look at another question. This one has angular velocity. Same idea. A fan blade is rotating at an angular velocity of 5 pi per second. Same one as before. If the tip of the blade is 20 centimeters from the center of rotation, at what speed is the tip moving? So we want to know, so we know that speed is a measurement of distance traveled compared to time. So we want to know, we need to know what distance the tip of the blade travels in a second. So that means we need to figure out what the arc length is. So arc length, length around the circle, or distance around the circle. So we're going to use this formula to calculate arc length. So we know the angle in 1 second is 5 pi, and we know the radius of the circle is 20 centimeters. So the arc length is 100 pi. So that means that in every second, the tip of that blade travels 100 pi centimeters. Hold on, centimeters. So it's 100 pi centimeters per second as a distance. Now, let's also get that as a decimal, just so it makes sort of maybe more sense. So this, I think, probably makes more sense to us intuitively, that every second that the tip of that fan blade passes through a distance of 314 centimeters. And of course, you could say 3.14 meters per second, whatever works. And so that's the speed at which the tip of the blade is moving. Another question, what is the angular velocity of a spinning object that makes 100 revolutions in 1 minute? So we have an object that's spinning and it makes 100 full circles in 1 minute, and we want the angular velocity. So we need to know what angle over time this object is spinning. So what do we know? It's 100 revolutions in 1 minute. So let's turn how many revolutions or rotations, and let's turn that into an angle. So 100 revolutions is 100 full circles, and every circle is 2 pi. So that is 200 pi in 1 minute. And that is an angular velocity statement. It's 200 pi per minute. Maybe we could reduce it. So let's reduce it to how many it is per second, which is 33.3 pi per second. But that's the angular velocity. So we took full revolutions and turned it into angle. Determine the velocity in meters per second of a point on the circumference of a wheel with a radius of 40 centimeters if the wheel spins 6 times per second. So the wheel is spinning 6 times per second. So it's rotating 6 times in 1 second. And we want to know the velocity of a point. So to find the velocity of a point, velocity or speed is distance over time, and distance around a circle is called arc length. So we need to find the arc length over a certain period of time. So we'll just say for now per second, because that's what we're given. We need to find the arc length. And in order to find arc length, we're going to use this formula. And that formula requires me to know the angle. So I need to take this wheel spin 6 times information and turn that into an angle. So again, we know that it's 6 full revolutions, and every revolution is a full circle, or 2 pi radians. Therefore, there are 12 pi radians per second is the angular velocity. So in 1 second, the angle will be 12 pi. So now I'm going to use this information, 40 centimeter radius, and calculate in 1 second what the arc length would be. So we know that arc length is equal to radius times the angle. I just rearranged. So if the radius is, hold on, I lost it. If the radius is 40 and the angle is 12 pi, then the arc length in 1 second, 40 times 12, is 480 pi. And that would be in the same units as radians, so centimeters, or more customarily for distances, let's actually get a decimal value. So this many centimeters, and so that would make sense to say 15 meters approximately. And let me just make sure I answer the question. So it's a velocity in meters per second, so 15 meters. So it's 15 meters. And all of my calculations were done in 1 second, right? So all of my information was per second. So it's 15 meters per second, and there's my answer. So I hope that's helpful in understanding a little bit more about radians and this concept of angular velocity and how it connects to rotations and arc length and speed. Okay, thanks for watching. Bye.